Hello everybody, my name is Ali Nejad. Let's please start the second lecture. Just a quick review. We are talking about the boundary layer equations over a flat plate, which is called Blasius flow. If you remember, at the end of the previous lecture, I derived or I simplified the boundary layer equations for you. When you can solve those equations successfully, at the end you will see these relationships for laminar flow. Delta x gives us boundary layer edge at each section as a function of x. And remember, in the denominator, Reynolds is a local Reynolds number. Then the total skin friction factor can be derived from this equation, and the total drag coefficient also can be derived from this equation. And in the denominator, Reynolds is the total Reynolds value, because the drag and skin friction coefficient are somehow meaningless at each point. It is calculated for the entire body. See, I can write it here actually for the drag formula as d 2d divided by rho u infinity squared a. So what, and a is the reference area. What you can see is this. There is one equation that can help us to find those values, and the other one is a definition. So from these equations, I can find CF and CD. Then I can use the definition. I can find shear stress and D. So at the very end, I can find tau of the wall and also drag with these equations. If I repeat the same procedure for turbulent flow, we can see these correlations. Delta as a function of x is 0.16 x divided by Reynolds of x to power 1/7. CF is 0.027 divided by the same Reynolds value, and CD is 0.031 divided by the same Reynolds value. So when the problem is given, we need to make sure that, we need to find that the flow is laminar or turbulent. Therefore, we can use this set of equations, or alternatively, this set of equations. So let me solve you one example to clarify what it is. So in this example, there is such a flat plate, and you can see that this is L, this is B, and this is U infinity. U infinity is given 6 meters per second. L and B. L is 1.1 is given. B is 0.55. Then the fluid properties are also given. Meter, they are meter. I am going to find these delta, CF, and CD. Or at the end, let's find drag force, because for any aerodynamic problems, any external flow problems, at the very end, we are looking for find drag force. When we say drag, drag means force. So I don't need to mention that. Let's put it in parentheses. First of all, I need to find Reynolds number. Reynolds number is, according to definition, rho u infinity L over mu. If you plug those values, rho for this problem is a specific type of oil, actually, 89161.1. And mu for that oil, that's SAE 30 oil, is 0.29. So the total Reynolds number, the value is 2,300. See, even though it's a big Reynolds number, very a huge Reynolds number. But the critical Reynolds number for flat plate is 10 to the power 6, the critical value. Therefore, the flow is laminar, still laminar. So I can use these correlations, and I can find CD from this equation here. Therefore, it's 1.328 divided by a square root of this Reynolds number, 2,000, 20,000, 300, which is 0.00933. Then, if I want to find drag FD, or just show it with D, in this case, I can use the definition, which is this one. So now I know the CD. Therefore, CD times by the denominator, and A is B times L. In that case, actually A is 2B times L, because there is flow at the top and the bottom of the flat plate. So the area is the top area and the bottom area. So when you use these values, the final value would be 181 Newton. Okay, this example shows you that how I can see. First of all, I need to find the Reynolds number for two reasons: to see the flow is laminar or turbulent, or which set of equations I need to use. Second of all, I still need the Reynolds number for the correlations for these equations. Then I can find the drag coefficient, and consequently, from the definition of the drag coefficient, I can find the drag force. In heat transfer, we will go over these topics very elaborately. We have thermal boundary layer in addition to velocity or hydraulic boundary layer, and that's where we talk about different types of boundary layer and correlations in that class.